The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
So the introduction, we know alkali silica reaction causes expansion, cracking and degradation of mechanical properties of concrete. On the other hand, fiber reinforcement is considered effective in bridging cracks and increase the tensile strength of concrete. So therefore, fiber reinforcement appears to be promising for reducing ASR damage of concrete. And there have been several studies, but most of them focus on the effectiveness of fibers in reducing the expansion and the degradation in mechanical properties of concrete. So my study is particularly focused on the microscopic cracking of ASR-affected fiber reinforced concrete, but I will still be presenting the expansion and mechanical properties result as well. So the mixed design of concrete was based on ASTM C1293 that is generally used for concrete prism test. So a reactive concrete mix was made by using sprat, which is a highly reactive aggregate as a coarse aggregate, and non-reactive sand. And alkali level was boosted to 5.25 kg per meter cube of concrete as per ASTM C1293. And 3 mixes were used. The first is the reference mix with no fibers, and second mix is the same mix with addition of 0.65% fiber volume fraction, and the third mix is same base mix with 1.3% fiber addition. Further to the 3 mixes, we had 2 variations in the first 2 mixes, that is mix with no fibers and mix with 0.65% fiber. So we cast concrete prisms which had longitudinal reinforcement at the center line of the prisms in some of the specimens. So accordingly, we had 5 test series. So M0.0P means mix with no fibers and is plain, meaning no reinforcement. And M0.0R means mix with no fiber but reinforced, and similarly. And from the 3 mixes, concrete cylinders were cast to test compressive strength and modulus of elasticity, and concrete prisms were cast to measure expansion, modulus of rupture, and damage rating index. All the accelerated conditioning of the specimen was performed at 50 degrees centigrade and greater than 95% relative humidity. The fibers used for the concrete were 30 millimeter long and 0.38 millimeter diameter to give the aspect ratio of close to 80. Now let's go to the results. First, longitudinal expansion. So this slide presents the longitudinal expansion of the 5 series. We can see that, so this is for the mix with no fibers, and that is plain, and that has the maximum expansion. And with increase in fiber content, the expansion is going down. And this is true for both cases of either plain or the reinforced case. So if we have increased fiber content, generally we observe lower expansion. And if we compare the series with fibers versus the series with reinforcement, the effectiveness of longitudinal reinforcement appears significantly more compared to the effectiveness of the fiber. So any inclusion of reinforcement as a continuous inclusion would be more effective to reduce the longitudinal expansion than the discrete inclusion such as the fibers. Next is the damage rating index. Damage rating index is a method that is used to basically quantify the damage due to ASR by counting the cracks ASR has caused in the concrete. So in this method, concrete sections are polished down to a surface roughness of approximately 5 micrometer, and the concrete slice is divided into several grids of 1 centimeter by 1 centimeter, and each grid is examined under stereo binocular microscope at a zoom level of 16 times magnification. Then 7 different crack features are counted for each grid, and the number of counts is multiplied by the weighting factor and summed, and then it is normalized to get the damage rating index value. This is how the DRI is performed. And before going to the results of the DRI analysis, here are some images while observed during the DRI analysis. So this slide shows the typical field of view of that 1 centimeter by 1 centimeter grid under the microscope. We can see some fibers here, and we can see there is some damage in the aggregate, but this does not look like a crack due to ASR, but there is still some damage. So this type of particle has been classified as disaggregated or disintegrated aggregate particle in this analysis. And this slide shows some fibers and cracks. So here we can see these black fibers. Some are circular because the fibers were perpendicular to the plane, and some fibers we see like elliptical. So depending on the orientation of the fiber, different orientations are observed in this plane. And here we can see some ASR cracking. The cracks have passed from aggregate and to the paste like that. And generally, by using fibers, we expect that fibers bridge the cracking. But there were some instances where we had observation like this. So it appears that this ASR crack, because it was intercepted by this fiber, it was branched into perhaps 2 cracks, and for this branching, the fiber must have played a role. So it is not always the case that fibers bridge the cracks, but they could actually sometimes increase the number of cracks, and that actually means the DRI value can also increase to some extent. And in this slide, we can see the air voids filled with alkali silica reaction product, both in concrete with no fiber and in concrete with 1.3% fiber. So there are many fibers here, and this ASR product is filling the air void. And in this slide, I want to show the confinement effect provided by the fibers. So the image in the left-hand side is from the mix with no fibers, and the image on the right-hand side is mixed with 1.3% fibers. And if we have a more close-up view, we can see some opened cracks in this condition. But in the case with 1.3% fibers, it's difficult to observe the open crack quite frequently. Rather, what we observed is some black, the black is the aggregate particle, that reactive sprat aggregate particle. It is filled with this white product. So that is actually the ASR product. And so the movement of this ASR product was confined, so it remained at the source where it was produced. And this indicates that there was less cracking in the aggregates, and because the ASR product could not move to the paste matrix, so there was less paste cracking as well. So this slide demonstrates that because of the fibers, there was a confinement effect which lowered the cracking of the aggregates as well as the significant lowering of the cracking of the paste matrix. And I did some thin section analysis and took images in optical microscope. And here on the top figure, we can see that the cross section of the fiber, and that is surrounded by the alkali silica reaction gel deposit. And here, this is the end of the fiber. So the end of the fiber probably because of the expansion, the fiber was pulled and there was some gap formed, and that gap was actually filled by the alkali silica reaction product. So for your information, so this is the plain polarized light image and this is the cross polarized light image. So that confirms that this material here is the alkali silica reaction gel. Now let's go to the DRI results. This slide shows the results at 28 days of accelerated curing at 50 degrees centigrade, but this one is the reference specimen that was cured at room temperature. So compared to the other 5 series which was cured at 50 degrees centigrade, this has significantly lower DRI, which we expect because temperature accelerates the alkali silica reaction. And among these 5 series, we can see that the mix with 1.3% fibers had the least DRI value, and also it had the lowest paste cracking. These two are the paste cracking, so we can see the lowest paste cracking over here. And compared to the mix with no fibers, the mix with 0.65% fiber and the mix with central reinforcement but no fiber had larger, greater DRI value. And this is attributed to the fact that because of the steel inclusion in these 3 mixes, the steel introduced some increased anisotropy compared to this mix. So increased anisotropy led to more cracking. And now if we go into 91 days, so that means most of the alkali silica reaction had already taken place. So in that case, the mix which had lower DRI during 28 days also had the high DRI value. So that indicates that the material there is also damaged, but the cracking was delayed because it had no restraints and it had relatively more isotropy compared to the other mixes with fibers and reinforcement. And in this case also, the mix with 1.3% fiber had the lowest DRI value. So the fibers were effective in reducing the cracking in that particular case. Now compressive strength for the 3 mixes at different ages. And compressive strength was slightly increased to significantly increased in this case. And increase in compressive strength due to alkali silica reaction is not uncommon, so it has been reported in literature. But the most significant observation here is this significant increase in compressive strength in mix with 1.3% fiber. And that must have happened due to the confinement of ASR product, which we already saw in one of the slices. That confinement effect due to densely distributed fibers caused the fluid pressure also to take some part of the compressive loading, so that actually contributed in increasing the compressive strength. And also because of the ASR expansion and the confinement, the fiber actually pre-stressed the concrete, so that also helped to improve the compressive strength of concrete. And next, modulus of elasticity. Modulus of elasticity is one of the properties of concrete that is severely affected by ASR basically. So, and that was the observation in this case as well. So we can see the drop in modulus of elasticity due to alkali silica reaction, but the maximum degradation was observed with 0.65% fiber content, and there was only 9% degradation in modulus of elasticity for mixed with 1.3% fiber. So the 1.3% fiber content actually helped to reduce the degradation in modulus of elasticity. And one more observation here, if we compare these black bars, which are the test results at 28 days at room temperature, so that means very little ASR had taken place in that case, so we can basically ignore the ASR effect there. So if we ignore the ASR effect, then we see a trend like the maximum modulus of elasticity was observed for the case of 0.65% fiber content. That indicates the optimum fiber content, which is a terminology used in fiber reinforced concrete, appears to be somewhere around this range. But if we compare the results at after 91 days of curing, so that means most of the ASR has already taken place. So the modulus of elasticity was the greatest for the mix with 1.3%. So this indicates that the optimum fiber content appears to be influenced by ASR. Actually, it goes to the higher side. And next is the modulus of rupture, and it is a common understanding that modulus of rupture is increased because of the inclusion of fiber, and that was observed in this case as well. So compared to the mix with no fibers, so these mixes with fibers have greater modulus of rupture. But in all cases, all three mixes, there was some degradation in modulus of elasticity due to alkali silica reaction. So compared to this is smaller. Compared to this is smaller. But 1.3% fiber volume fraction completely offset the ASR degradation of modulus of rupture. So if we compare the modulus of rupture of mix with no fibers, the modulus of rupture of mix with 1.3% fiber, even after ASR degradation, is quite large. So undoubtedly fibers were useful to increase the flexural strength of concrete. So to conclude, DRI method can be used to investigate the cracking of fiber reinforced ASR affected concrete, and DRI method was able to demonstrate the lower paste cracking due to 1.3% fiber volume fraction. And fiber volume fraction of 1.3% was particularly effective to reduce longitudinal expansion, to reduce cracking, to reduce degradation in modulus of elasticity, and to completely offset the degradation in modulus of rupture. And fibers exhibited a tendency of optimum content, so in which 0.65% fiber was not adequate to reduce the ASR damage, but 1.3% fiber volume fraction was quite effective. And fibers provided confinement of ASR product that limited the movement of ASR product from the aggregate to the paste, and that's how the cracking was also reduced. And there were many instances in which the interface between fibers and concrete was filled with ASR products. And we would like to acknowledge the support provided by my professor's research grants. So thank you, and if you have any questions, please.
I have two questions. The first one is, you used 15 degrees Celsius to accelerate your ASR.
Yes.
Which may not represent the active condition outside. If you have any comments on how to meet the laboratory result with the physical happening ASR on site?
Yes, that's a good question. Actually, because alkali silica reaction is a very slow reaction, and in field concrete it takes maybe 10-15 years sometimes to show its effect. That's why the usual practice is to have accelerated tests. And among the accelerated tests, 38 degrees centigrade concrete prism test is considered more standard. And 50 degrees centigrade we chose is to further accelerate. And during my PhD study, I had one topic which compared the response at 38 degree and 50 degree centigrade. So we have published one journal paper based on that, and based on that result, at least for the sprat aggregate, we can say there is insignificant difference. Of course, the reaction is accelerated, but the level of expansion or the level of degradation, those things have insignificant effect compared between 38 and 50 degrees centigrade. And when it comes to the field condition, then it will again be, we haven't compared it with field, so I cannot say for sure, but by having that comparison between 38 and 50, and by having very little difference between those two, what we can say is it should be generally safe to interpret these results to field concretes also.
Doing more study to incorporate this nice reserve practice. That is what we found.
Yes, yes.
The second question is, one of your images demonstrated cracking of concrete, and how would you know whether it cracks are from ASR or something else, such as dry shrinkage or homogeneous cracks?
For that purpose, in this particular study, I didn't do the non-reactive concrete, but before this experimental series in my PhD, I had just to confirm that purpose. So I had cast a non-reactive control sample, and I performed the DRI analysis on them also. So based on those results, there were not many cracks there. So based on that result, I moved. Okay, these are due to ASR. Okay, thank you very much.